All right, let's dive right in. When you push Albert Einstein's math to its absolute breaking point limits, you get some of the weirdest, most mind-bending predictions about our universe you can imagine. We're going to go on a journey through his equations, starting with a classic, head-scratching puzzle about black holes.
Now, that sounds like a simple question, right? But the answer, it turns out, depends completely on where you're standing. Let's say you're watching a friend, a very brave friend, take the plunge. From your safe spot, far away, you'd never actually see them cross that point of no return.
So, from your point of view, as your friend gets closer and closer to the black hole, you'd see them start to slow down. The light from their ship would get stretched out, getting redder and dimmer, until they just kind of stop, seemingly frozen right on the edge for all eternity. This is the famous frozen astronaut paradox, and it's one of the strangest things to come out of general relativity. So, to really get why this happens, we need to break down exactly what you, the outside observer, would see, step by step. It's a whole process that unfolds as something gets closer and closer to that cosmic cliff edge. So you've got this sequence, slowing down, getting redder, fading out, and then just freezing. What in the universe is causing this incredible distortion of time? Well, the answer lies in how Einstein completely tore up the rulebook on gravity. He didn't just tweak the old ideas, he threw them out and started over.
See, this paradox isn't just some little mathematical quirk. It comes directly from the very heart of Einstein's theory. And to get it, we've got to go back and look at how he totally reimagined what gravity even is.
For hundreds of years, Newton's idea of gravity worked great. But you know who it really bothered? Newton himself. He couldn't stand the idea of some invisible force just reaching out across empty space instantaneously. He thought it was just plain absurd.
And that's the problem Einstein solved. He said, hey, what if there's no spooky force at all? Instead, mass tells the fabric of space-time how to bend and curve. And that curved space-time tells mass how to move. So the Earth isn't being pulled by the sun. It's just following a straight line through a universe that's been warped by the sun's immense gravity. But here's where it gets wild. When other physicists started actually solving Einstein's beautiful equations, the answers they got pointed to things so strange, so bizarre, that even Einstein himself was like, no way, that can't be real. It kicked off a debate that went on for decades.
And the first big crack in the dam came just a year after Einstein's theory was published. It came from an astrophysicist named Carl Schwarzschild, who was actually serving on the front lines of World War I while he was doing this math. His solution was brilliant, but it had these two spots where the math just went haywire and broke down completely. Now, it's that second problem spot, the one right at the event horizon where the math blows up, that fueled the whole paradox. I mean, if time literally freezes there according to the equations, how could a star ever finish collapsing to make a black hole? It looked like a huge flaw in the theory.
The big aha moment actually came from J. Robert Oppenheimer, way before he became famous for other reasons. He basically said, look, the paradox is just for the person watching from far away. If you're the one falling in, you just sail right on by without even noticing. The problem wasn't with reality. It was with the description of reality. The math only seemed to break because the coordinates, the map, that Schwarzschild used just wasn't the right tool for the job. You know, it's kind of like trying to draw a round planet on a flat piece of paper.
We've all seen those Mercator maps in school, right? Where Greenland looks like a giant continent as big as Africa. The map is useful for sailing, sure, but it totally distorts the sizes of things. Well, Schwarzschild's map had a similar distortion at the event horizon. All physicists had to do was choose a better map and poof, that mathematical problem at the edge just vanished.
And this is the part that just completely bends your brain. With the right map, you see that the singularity at the center isn't a place you can go to. It's a moment in time. It's the future. It's the end of the road for anything that falls in. But what's even crazier is that this new, complete map revealed other things that are somehow even stranger than a black hole.
Because when you take the math for a simple, perfect, eternal black hole, and you follow it as far as it can possibly go, you don't just get a black hole. Oh no, you get a whole cosmic menagerie of weird theoretical objects. First up, you get a white hole. If a black hole is a one-way door where you can only go in, a white hole is a one-way door where you can only come out. It's literally the movie of a black hole played in reverse. But that's not all. The math also suggests a destination for all that stuff coming out.
Yeah, you heard that right. The full solution points to a second, whole other universe, completely separate from ours. It's like the equations are saying, hey, if this universe exists, then mathematically this other one must exist too. And they're connected.
And that connection, that little throat between the two universes, that's what we call an Einstein-Rosen bridge, or what science fiction made famous, a wormhole. It's a theoretical tunnel through space-time. But, and this is the big question, is any of this real? Or is it all just ghosts hiding in the math?
Okay, let's bring it back down to Earth for a second. While all of this stuff is mathematically sound for a perfect, idealized black hole that has existed forever, these ideas hit some pretty major roadblocks when you try to apply them to the real, messy universe we actually live in. There are a couple of huge problems here. First, our universe isn't filled with eternal black holes. It's filled with black holes that formed when giant stars died. This math doesn't apply to them. And second, even if they did exist, that wormhole bridge would be incredibly unstable. It would snap shut so fast that not even a beam of light could make it through.
So this table pretty much sums up where we stand right now. Black holes, yeah, they're real. We've taken pictures of them. But white holes and stable, traversable wormholes, they seem destined to stay in the world of science fiction, at least for now. But before we close the book on them completely,
We have to remember this. For decades, the smartest physicists on the planet, including Einstein himself, thought black holes were just nonsense. They thought nature would find a way to stop them from ever forming. And they were wrong. Our understanding is always changing, always growing.
And that leaves us with one last, really tantalizing question to chew on. The universe has proven us wrong before. These wild predictions from Einstein's math show us just how much more there could be out there, hiding just beyond our understanding. What idea that seems totally impossible today might just be tomorrow's reality?